Welcome to Climate Planet. The climate of the Earth is changing. This has happened many times throughout the planet's history, but is now increasing rapidly. I'm going to give you a historical overview of how the climate has changed up till today, when we're experiencing rising temperatures, extreme weather conditions, ice caps melting, and sea levels rising. Today, there are almost 8 billion of us humans on Earth, and in just 40 years, the number is estimated to reach 10 billion. We all need water, food, and energy. Therefore, we must find a solution that on the one hand protects nature, but at the same time provides energy and resources for everyone. Solutions already exist, but they need to be applied on a global scale. This is one of the greatest political, technological, and economic challenges the world is facing today, and will be facing in the years to come. But first, a glance at the past. The universe was created 14 billion years ago by a massive explosion called the Big Bang, which subsequently formed galaxies, stars, and planets. The formation of our solar system began 4.5 billion years ago, when a vast cloud of cosmic dust particles was compressed by gravitational forces. In the center of the cloud, molecules crashed together tightly and created what we know as the Sun, whereas the particles further away from the core became planets. Among these is planet Earth, the third planet from the Sun. In the beginning, the Earth itself was very warm and fluid, but surface temperatures slowly dropped and created a hard crust. The crust of the Earth was not just one big shell, but split into larger areas known as tectonic plates, which are floating on top of a layer of liquid rock, kind of like styrofoam pieces on water. The tectonic plates are constantly moving, and thus Earth's oceans and continents are being perpetually redefined. Approximately 200 million years ago, all the plates were combined into one supercontinent called Pangaea. Later, the supercontinent began breaking up and created the Earth as we know it today. In certain areas of the world, the tectonic plates pull away from each other, whereas in other parts the plates are moving closer together and even colliding. In these areas, the Earth is very active, which causes both volcanic eruptions and earthquakes. Here is an overview of all the earthquakes occurring between 2001 and 2015. It clearly shows where the rupture zones and the tectonic plates are located. Sometimes the collisions between the plates are very dramatic. An example would be 50 million years ago, when the Indian plate crashed into the Asian plate. This hard collision created the mountains of the Himalayas. This area is continuously active and triggers earthquakes on a regular basis. Most recently, the earthquake in Nepal in April 2015. It's common knowledge that the climate of the Earth has been fluctuating between Ice Age and interglacial periods. Right now, we're experiencing an interglacial state. There are more reasons behind the formation of the Ice Ages. It is closely related to the Earth's orbit around the Sun and the tilt of the axis of the rotation, which has been changing over thousands of years. This is due to mutual attractions between the rest of the planets in the solar system. As a result, the orbit of the Earth periodically stretches into an elliptical shape. When the Earth is orbiting further away from the Sun for longer periods during the year, the globe is turning colder and the ice is spreading, resulting in a new ice age. The ellipse-shaped path around the Sun is slowly becoming more and more circular through thousands of years, and the ice will melt once again, creating a new interglacial period. Ice core drillings on Antarctica can trace data 600,000 years back in time and show that the ice ages last for approximately 100,000 years, whereas the interglacial periods last for about 15 to 20,000 years. Additionally, the ice core shows the atmosphere's natural CO2 level during the Ice Age period, which is estimated to be around 200 ppm in contrast to 280 ppm during the interglacial periods. ppm is an abbreviation for parts per million, meaning that for every million air molecules, you'll have 200 molecules of CO2 under the Ice Age and 280 in the interglacial periods. Even though these numbers do not seem that high, the increase is enough to keep temperatures about 30 degrees higher than if there were no greenhouse gases. Until the Industrial Revolution in the 19th century, the number was in fact 280 ppm, but after that it started to increase. The climate of the Earth has been fairly stable since the last Ice Age. We have experienced fluctuations in temperature, but the climate has been stable enough for life and civilizations to develop. In the early 18th century, Thomas Newcomen succeeded in creating a steam engine. This invention was beneficial for the English mining industry, which was now able to remove water from deep mine shafts. The Industrial Revolution started accelerating when the Scotsman James Watt improved the steam engine in 1774. The burning of fossil fuels such as coal could now create energy to make the production industry more efficient and became a starting point for the development of the railways. Now, steam locomotives could transport goods and people greater distances in a shorter period of time. In the meantime, researchers increased their interest in nature and the atmosphere surrounding us. In the 1820s, the French mathematician Joseph Fourier was wondering about the warm temperature of the Earth. He knew that the planet was radiating energy towards outer space, and this enabled him to come up with the theory that something was trapping energy, just like a greenhouse. He just didn't know quite how. The answer came in 1861, when the Irishman John Tyndall was able to explain the greenhouse effect after a few lab experiments including carbon dioxide and water vapor or steam. The greenhouse effect is central for our understanding of what is happening to the climate today. The sun is extremely hot and releases its energy in the form of short-wave radiation. These waves can generally pass unhindered through our atmosphere and reach the ground surface, where the energy is used for heating, vegetation, and life itself. This is different from the Earth's radiation, as we know on cold, clear nights. The temperature of the Earth is much colder compared to the Sun, which creates long-wave radiation. The globe is simply cooled down because of the long-wave radiation emitted by the Earth and sent back to space. But unfortunately, it is not that simple. The long-wave radiation is captured by greenhouse gases such as carbon dioxide, methane, nitrous oxide, and of course water vapor. The greenhouse gases do not absorb the radiation, but instead reflect it in different directions, which means that some of the Earth's radiation is redirected back to the ground surface. In reality, the greenhouse gases can be seen as a blanket surrounding Earth because they keep the planet warm. When we burn fossil fuels such as coal, oil, and gas, we're emitting more and more greenhouse gases into the atmosphere. Consequently, the blanket surrounding the Earth becomes more efficient in keeping the globe warm, and therefore the temperature rises. This is exactly what has happened in the past several decades. This fact has been known for the last 150 years, and the consequence of burning coal was described by the Swede Svante Arrhenius, who in 1896 calculated that a twofold increase in CO2 in the atmosphere would cause a temperature rise of 5 to 6 degrees Celsius. Unfortunately, nobody believed him at the time. The increasing amount of CO2 in the atmosphere causes a rise in temperature. It's more than just a steadily rising temperature curve. Yearly variations in weather conditions play a huge role as well. Therefore, we generally look at average temperatures over a longer period of time. If every year you calculate the average for the past 5 years, you'll get what's known as a rolling 5-year average. And it's quite clear that there is a rising trend. The ever redder color of the Earth also indicates that temperatures are rising. Until the 1970s, the temperatures were increasing rather slowly, especially in the period following World War II, when temperatures stagnated. We experienced a fairly stable temperature rise until 1940, followed by a small drop in temperature when there was even talk of the possibility of a new ice age. A possible explanation for the temperature drop could be the increased levels of sulfur pollution in the air caused by industry, because pollution increased after World War II and was blocking the sun's radiation. But this theory is not yet proven. We know that one of the consequences of the heavy pollution was acid rain. It became clear during the 70s and 80s that pollution was particularly unhealthy and that the rain was starting to contain sulfuric acid, which had serious consequences for the pine trees. Filters for chimneys were developed so that pollution could be reduced significantly. At the same time, the temperature again started rising globally, which it has mostly continued to do ever since. But let's concentrate on CO2, carbon dioxide. The concentration of CO2 in the atmosphere has been measured in Hawaii since 1958. The curve is called the Keeling curve and is named after Charles David Keeling, who initiated the measurements. The concentrations ought to be at the same level as in the interglacial periods, meaning 280 ppm, and were until industrialization began in the 17th century. Today, however, the number is 415 ppm, an increase of almost 50%. But the concentration and emission are not consistent throughout the globe. It's obvious that areas which are highly populated and have large industry will have higher emissions and greater concentrations of CO2. North America, Europe, and Asia are the largest contributors of CO2 emission to the atmosphere. Wind circulation in the atmosphere is distributing CO2 to the entire globe. But there are also seasonal variations in the concentration of CO2 in the atmosphere. During the seasons spring and summer, CO2 levels decrease because of the increased utilization of CO2 by plants and trees in the growing season. They absorb the CO2 and use the carbon to build plant fiber, while oxygen is returned to the atmosphere, where we humans can benefit from this life-essential resource. When plants are growing, they utilize CO2 and the concentrations drop. It is the opposite case during autumn and winter, when most plants stop growing, resulting in a rise in CO2 concentrations. CO2 is most commonly discussed, but there are other important greenhouse gases which contribute to rising temperature levels. Methane and nitrous oxide are among these, and their quantity has been increasing during recent years. As a greenhouse gas, methane is approximately 30 times more powerful than CO2, and nitrous oxide is as much as 300 times as strong. Even though water vapor and CO2 are the most crucial greenhouse gases, methane and nitrous oxide are becoming more and more important. Methane is produced, amongst other things, by livestock and during rice production. This means that the more cows there are, the more methane is released to the atmosphere. Furthermore, the increasing temperatures are causing the permafrost at the Arctic to melt. When this happens, organic material, which was formerly preserved in ice, starts to rot and release additional greenhouse gases, amongst them methane. The permafrost is frozen and hard as stone all year round. Therefore, people have built houses, roads, and pipelines on top of the ice. When the ice starts to melt, the roads will become bumpy, the houses will crack, and pipes will break. On top of everything I just mentioned, we must not forget that the high temperatures are accelerating the evaporation of the oceans and the surface of the Earth. Additional water vapor contributed to the atmosphere, and water vapor is a strong greenhouse gas. All in all, The rising temperature is creating a self-reinforcing effect with an extra supply of different greenhouse gases. Since 1970, we've experienced a global increase in temperatures of about 0.7 degrees Celsius. This doesn't sound like much, but as it is a global average, the figure obscures large variations. The greatest increase is seen in the Northern Hemisphere, especially in the Arctic region. The Southern Hemisphere mainly consists of water, which is only slowly getting warmer. However, Australia is now considered a dark red continent. Today, the oceans have been coloured red because global warming has gained more power. This is of great importance. The temperature of the ocean is not only determined by the heat of the surface as it is on the ground. In the ocean, the heat is distributed to every corner of the sea, which can hold on to enormous quantities of heat and keep the temperature up if it should be needed at another point in time. Some years, temperatures rise more dramatically due to El Niño, a naturally recurring phenomenon that, among other things, increases the sea temperature off the coast of Peru. It was particularly strong in 2015-16, when global temperatures reached record highs. In an El Niño year, weather is unusual in many parts of the globe. In these years, great quantities of energy are transferred into the atmosphere. Because of general global warming, it is difficult for the atmosphere to get rid of this energy, which is how El Niño ends up contributing to climate change. It is noteworthy that global temperatures in 2020 are approaching the record highs from 2016, but now without the help of El Niño. The consequences of the rising temperature are endless, and the vast majority of these are negative. We've already seen significant changes in weather conditions. As a general rule of thumb, wet and rainy regions will experience larger quantities of rainfall, while dry areas will become drier. This correlates with rising temperatures, which will increase evaporation. The vaporized water will be transported by winds to the areas where it is already raining. At the same time, the clouds will become more intense, since the vaporized water is accompanied by heat which is released to the sky when raindrops are formed. As a result, we're experiencing more instances of heavy rainfall on a global scale, which leads to flooding. The elevated ocean temperatures have huge impact with regard to tropical hurricanes. Hurricanes feed off vaporized water from the sea, so when the temperature increases, hurricanes are energized. This was the case in November 2013, when the typhoon Haiyan hit the Philippines and massive destruction followed. The water to the east of the islands was warmer than average, which provided Haiyan with extra energy right before it hit the islands. Back in 2005, the Hurricane Katrina struck New Orleans, the surrounding levees collapsed, and the city was completely flooded. This meant that the discussion about global warming was now on the political agenda in the US. The number of tropical hurricanes varies greatly from year to year, as they're dependent on both sea temperature and the state of the atmosphere. In 2017, atmospheric conditions were conducive, and as the sea temperature in large parts of the Atlantic Ocean exceeded 30 degrees, many tropical hurricanes formed in this exact area. Hurricane Harvey put Houston underwater on around the 1st of September, bringing with it around a meter of water in just a few days. Soon after, several Caribbean islands were almost razed to the ground, as both Hurricane Irma and Hurricane Maria hit within a few days of each other. Both hurricanes were in the most powerful category, and the devastation made several islands almost uninhabitable. It is unlikely that the number of future hurricanes will increase, but they will instead grow in severity and power, since sea temperatures are expected to continue to rise. Sea temperatures also influence storms. Storms are more active in northern latitudes, and during the months of autumn, northern Europe is at particular risk. Even though factors such as the Arctic ice starting to melt play an important role in the discussion of global warming, scientists have forecast that northwestern Europe will experience more powerful storms than the ones we've experienced in the last couple of years. The consequences are dependent on the direction of low-pressure conditions, but it might put pressure on the levees facing the ocean. The ice is melting, and the ocean level is rising. This must be the most spectacular evidence of the rising temperature. Yes, ice is melting when the temperature rises. The ice is bound to glaciers in Greenland and the two polar regions. Generally speaking, the ice is melting everywhere to some extent. The glaciers have always regulated the Earth's temperature, like a sort of thermostat. The white surface reflects the sunlight back to space and does not take part in the global energy audit. When the ice melts, the white surface is replaced by open water or soil, which attracts more energy compared to before the glaciers had melted and creates its own self-reinforcing effect. In the Arctic region around the North Pole, the ice is decreasing day by day. This is both in a horizontal perspective but also in total volume, which is an indicator of how thick the ice has become. The thinner the ice, the more easily it will melt. It is only a matter of time before the North Pole remains free from ice during the summer period. Greenland's ice cap is continuously melting, and if the temperature continues to increase, the melting might accelerate. It is also the case in Antarctica, but here the severity of the situation is less clear. The west part of Antarctica, facing towards South America, is experiencing high levels of deglaciation. The situation is more complicated in the East Antarctic, where the results are also not clear. However, the latest scientific research indicates that the ice cap here has become more unstable, and more ice is breaking off into the ocean. The melting ice in the Arctic regions is catastrophic for the animal kingdom, in particular the majestic polar bear. The ice is of great importance when polar bears go hunting for seals. The thin ice can easily break into smaller pieces, leaving polar bears stranded and drifting off into the sea. If the ice continues melting at the same pace as now, up to 30% of the current polar bear population could disappear. Aside from regulating the Earth's thermostat, the melting ice is causing the ocean level to rise. This is also a consequence of the general increase in sea temperatures. Warmer water simply occupies a greater volume, and half of the rise in sea levels is caused by precisely this increase in temperature. Scientists anticipate the sea levels to rise by at least half a meter, but conceivably even more, meaning that all cities around the world will be vulnerable to coastal flooding to an extent we don't yet understand. New York was hit by tropical Hurricane Sandy in November 2012 and suffered extensive flooding due to a 4-meter-deep storm surge. By the middle of this century, the sea is expected to have risen by a further half-meter. A half-meter sea level rise would only have a minor impact on Manhattan, as you can see here. But when coupled with the effect of a Hurricane Sandy-level storm, the picture suddenly becomes more dramatic. Another consequence of the deglaciation of Greenland, among other places, is the possible impact on the Gulf Stream, which is keeping the temperature stable in northwestern Europe. The deglaciation originating from Greenland contributes large quantities of fresh water to the ocean, reducing the salt concentration and thereby making it lighter. This can affect the water's buoyancy in the sea surrounding Greenland. This mechanism is keeping the Gulf Stream alive. The Gulf Stream will weaken, and this will affect wildlife in the sea, producing a colder climate in northwestern Europe. Since humans' natural habitat is above sea level, we're often unaware of what is taking place underneath the surface of the sea, even though it is very important for the absorption of the CO2 we emit. In fact, the ocean absorbs nearly 30% of CO2 emissions, but this has consequences. Back in 1880, When the atmosphere contained the anticipated content of CO2 of 280 ppm, the ocean looked blue and healthy. But when CO2 reacts with water, it creates carbonic acid, a reduction in the pH value, and the ocean becomes more acidic. This has a consequence for all living organisms who are using the calcium as building blocks. Everyone knows that you can use different acids to remove calcium from a coffee pot. More acidity in the ocean will therefore impair living conditions for crustaceans such as krill. Krill is excellent feed for both penguins and whales. But since the number of krill in the ocean has declined 80% in the last 40 years, it is threatening the very population of both species. The acidity levels in the oceans have a great impact on the well-being of the coral reefs, which are in poor condition worldwide. Both the acidity and the elevated temperature of the sea are killing the coral. Coral is very sensitive to its living conditions. In the latest episode, extreme El Niño-generated high temperatures in the sea surrounding Australia meant a large part of the Great Barrier Reef, the world's largest coral reef, was destroyed, leaving the reef almost extinct. The temperature has now dropped, and the reef is starting to restore itself. Some areas are starting to succeed, but the acidity and the temperature rise in the ocean are still present, and the reef might not recover completely. Now that we're discussing the tropics, we can see that tropical regions are starting to expand further, both south and north. This means that everything connected to tropical nature will expand as well. This might seem rather exotic if you think in terms of the plant and animal kingdom, but quickly becomes problematic when you take tropical diseases such as malaria and the dengue fever into consideration. Certain mosquito species which can carry these diseases have been tracked to northern regions such as New York and Denmark. However, none of the traced individuals were carriers of the diseases. Many of the Earth's deserts are located at the border of the tropical belt. With the current expansion of the tropical regions, the desert's areas are most likely to increase as well. In relation to Europe, this means that the Mediterranean region is at risk of drought and potential desert. This will also mean an increased risk of forest fires. The European drought in 2018 caused several forest fires in Sweden and elsewhere, and Australia suffered widespread forest fires after a long drought in 2019. Forest fires are an intrinsic part of the cycle of nature, but climate change is causing them to become more frequent, and they may appear in areas that are not used to forest fires. The tropics are also home to the rainforests. In recent decades, large areas of rainforest have been cut down or destroyed to provide room for palm production or grazing area for livestock. The wood is burned after it has been cut down instead of putting it to use, which contributes additional CO2 to the atmosphere. The clearing of large areas of rainforest has made life difficult for many species. The orangutan is threatened with extinction, not only because of the missing trees, but also because of forest fires due to drought or because of flooding due to extreme rain. These are all factors that are threatening the survival of the orangutan. In Central Europe, climate change is clearly visible, with a change in rainfall and more torrential rain. Rising temperatures are changing snow conditions in the Alps, meaning skiers need to go ever higher to find good slopes. On the other hand, more snow is falling, which matters during the spring when the snow melts. If the snow melts too rapidly, meltwater will fill the rivers up, leading to a greater risk of flooding. In Northern Europe, winters are now milder and wetter. We saw this in January 2020, when Denmark suffered severe flooding. When temperatures are low, evaporation is minimal, so the water sits in ponds on the fields until it slowly drains into the gradually rising groundwater. Agriculture must adapt to the new climate. Crops will need to be replaced with others in some places, and there is the risk of longer periods of drought and heat waves, increasing the need for irrigation. Along the coasts, rising sea levels are a major challenge. There is the risk of seawater ingress, which destroys fields, meaning dikes need to be extended. So there are good reasons why Europe is focusing a lot of its efforts on adapting to the new climate while trying to stabilize the climate in the longer term. So what then is the solution to all of these problems? There's no doubt a solid and stable solution must include the entire globe. And it's therefore under the UN we must find the answer. The UN is dealing with climate from both a scientific and political perspective. The scientific work is dealt with by the UN's Panel on Climate Change, which was founded in 1988. The panel consists of approximately 2,500 researchers, who every 5 to 7 years issue a report on climate change. The updated research will then be received by the political system, which is working based on the Convention on Climate Change established in Rio, Brazil back in 1992. The Convention, which is carefully worded, states that the countries agree upon stabilizing the atmosphere's content of greenhouse gases to such a level that dangerous man-induced climate changes are prevented. A part of the Convention states that the countries have to meet once a year to discuss the condition of the climate and potential solutions. The meetings are called COP, which is short for Conference of Parties. COP1 took place in Berlin in 1995. COP3 was held in Kyoto, where the Kyoto Agreement was established. The agreement was never fully implemented. One of the reasons it was not implemented was that the USA did not want to participate. The UN's Panel on Climate Change bases their work on different models of the future. And the worst possible scenario is the one where the world consumes coal, oil and gas in exactly the same way we do now. A scenario where we don't take climate change seriously, but instead are controlled by economic perspectives, what we call business as usual. This will cause the temperatures to rise all over the globe, as we also experience here. Global warming involves the entire population. Therefore, the UN are aware that we need a good and global climate treaty in order to reach a solution. The intention was to form a new global treaty during COP15 in 2009 in Copenhagen. But even though expectations were very high, unfortunately the parties didn't manage to reach a consensus. They did succeed in 2015 under COP21 in Paris. Even though the Paris Agreement doesn't solve the climate problem once and for all, there is reason to be optimistic, simply because the countries were able to agree that the temperature rise should only be allowed to reach a maximum of 2 degrees Celsius compared to 1850. The temperature has already increased by 1.1 degrees, so new solutions are extremely urgent. The Paris Agreement includes promises of restrictions in greenhouse emissions. This is a part of the climate plans which many countries have formulated. Research shows that if we do not take more action, the global temperature will increase by 3 to 3.5 degrees Celsius, which is 2 degrees more than the number agreed upon in the climate agreement. Therefore, the Paris Agreement must be improved. It is also on the agenda of future negotiations. This is about following the positive scenario from the UN's Intergovernmental Panel on Climate Change, where greenhouse emissions decrease rapidly by at least 25% before 2030 to keep the increase in temperatures below 2 degrees. If we manage to succeed with these scenarios, we do have a fair chance of adhering to the maximum limit of 2 degrees. The temperature will still increase, but at a more moderate pace, so hopefully mankind can cope with the changes. This involves new technologies and new business adventures. One of the positive outcomes of COP21 in Paris was the movement of investments over to the development of the technologies required. This has the potential to transform our towns and cities into clean, green oases, where the energy required comes from renewable energy sources. Planes and ships will use fuel that does not emit more greenhouse gases into the atmosphere. This very technology is being developed as we speak. Our food will still be produced in open countryside using sustainable production methods, but also in skyscrapers, where it is easier to limit the emission of greenhouse gases. This is a vision of the future that Climate Planet is all about. Namely, the fact that it is possible to create a better future as long as we believe in it and everyone works together. It's not enough if I try to make a change or if you do. We have to work together. Together in the family, with our neighbours, the whole street, the city, the country. The whole world must work together. Our efforts will be for the greater good of future generations, our children and grandchildren.